In a series of next few videos, we'll optimize a portfolio objective with an objective of maximizing Sharpe ratio. Now, the theoretical underpinnings of Sharpe ratio have already well discussed. Here we have a combination of return for a per unit of risk, or what we call as price of risk. That is per unit of risk, how much risk return risk premium is there. So we maximize the Sharpe ratio object, often a very important measure of fund managers. So we'll try to see how to optimize against around this objective function. So first we'll set the objective function as Sharpe ratio. So we'll create a objective portfolio object with this Sharpe ratio. How to do that? We'll again use of add dot objective. Now first recall that there are two objectives combined. So first is, we'll again start with our portfolio initiation objective, initiate portf. But first we'll specify the objective type as return with name as mean. So that is first. Now in the next step, I'll add another constraint to this object, portfolio object, and we have been doing this already, but in this case, in this particular case, previously also we saw how to add two portfolios, so this is not new to us. But in this case, we'll keep that objective as a part of optimization process. So see, I'm adding type as risk. Now I have added another objective name. In this case, because we are using Sharpe ratio, the risk appropriate risk measure is standard deviation, but I'm not using that parameter or feature as multiplier equal to 0. So now the standard deviation will remain part of optimization process, and therefore if I print this sr.portf, you would notice when I print this, this contains all the constraints, but now we have two objectives. My bad, I should have used this sr.portf here so that both the objectives are added. So now you have two objects here, mean as well as standard deviation. So now you have two objectives, and now when it is optimized, the return will be on numerator, risk will be on denominator. So you will get something similar to Sharpe ratio, or exactly the Sharpe ratio. Now we'll start with the optimization process. So I'll not rewrite the full code again. I'll just borrow from the previous optimizations. So let us go back to the optimization with three optimizers, and we'll copy these codes with a very little adjustment. The same codes can be reused rather than rewriting the entire thing. So for example, here we have as minimum ES as objective. So we'll use minimum SR. Now there's a small tweak that is needed. So now that we have put it as the objective as maximize SR, maximize our SR, we will add one more argument to this entire code, which is to enable this kind of numerator denominator optimization. Max SR equal to true. Let us put as trace also equal to true. So generally when you put trace also is true, all the computations are saved, all the computations that are happening are saved. So let me run it. So let us run this kind of optimization. Again here max instead of min ES, we'll make use of our sr.portf objective. We have already created this objective, and while the optimization schedule runs, let us put our, so we can see the weights 9.3 or 9.4% to Bitcoin, 19.7 to S&P 500, ESG fund as the minimum 5%, and 66.93 to EA futures. We can also print the whole object. We can see here the expected return as close to 0.14 and standard deviation as 2.2. So this is our complete object. Now the same thing we'll do with our max SR d-optim objective again. So d-optim also max SR. Here again sr.portf, we'll replace it with sr.portf. Now recall that we have added these two, this additional. So trace is already set as true. All we need to do is this max SR equal to true. Other parameters such as search size and other things are already there, so we'll just keep them as it is. And while the optimization takes place, we'll just tweak our code. So let's see what weights we get. So 5% for Bitcoin, 6.6 for S&P, ESG fund has 79 and 8.4 for UA futures. You can print your full objective. Again, the expected return is 0.04% close to, and risk is 1.25%. So now the last is random portfolio. Again, as we have been doing, we'll tweak the name and reuse the existing code. We need to add this maxsr argument as true. So we'll add this maxsr argument as true. Also, do not forget to change or replace. Generally, this is the mistake. We tend to miss this part. We need to replace this sr.portf as portfolio object. And while the optimization takes place, will let us tweak the object. So it may take a few seconds to optimize. You can see the red box here running, which means the code is still running. So let it run. Depending upon the speed of your computer, it will take some time. And now once it is done, you can see the output: 5% for Bitcoin, S&P 500, again the minimum weight. We have already set the constraint. So constraint is minimum 5%. AG fund is 82%, and your future. So across the three optimizations, you can see the weight changing and also the risk measure changing, though there's not much change in terms of overall expected return at close to 0.035% and risk at 1.2, but still there are minor changes across different optimization schedules. So in this particular video, we saw three different optimizations and the different weights that we are getting. There were some minor differences, but at the overall level, we can see the return and risk is quite similar for all the three optimizations. In the next video, we'll see the visualization of these three optimized portfolio objects that we have created. In this video, we'll visualize the portfolio objects. First, we'll visualize the portfolio weights. So let us start with that. So path and row. Now since we have three portfolio objects, and again we'll make use of our chart.weights, and we have already created this maxsr objective. Maxsr, first we'll use maxsr, and the central heading is maximize Sharpe ratio with ROI object. Now all I need to do is just copy paste it, and the second object is D with doptim, and the third objective of ours was to use random portfolio based optimization. So now we have written the code, so let us visualize. So let us zoom in on our three objects. With ROI optimization, we have UA futures as almost 65% weight, close to 70% in fact, and smaller weights to Bitcoin, in fact very close to 5% to ESG fund, which is our minimum threshold, and then some close to around 20% to S&P 500. But if you contrast it with the doptim and random portfolio optimization, so here you can see the highest weight close to 80% is given to ESG fund, while very small, very close to 5 to 7% weights to other securities. So there is certain difference. Let us again use our bar chart based method. So now we'll visualize with bar plots. The same set of codes, only I'll tweak them in a minor fashion. So I'll just add plot.type as bar plot. There are some other types which you can check with question mark that I have argument that I have already shown. Here you can add legend.loc as null. Now you can just simply copy paste it in the other three codes also, to say in the interest of time. And now I'll help you visualize. So I'll just run this. So you can see again the same result, but in a different way of representation. It looks very nice aesthetically. You can see here that UA futures has a very high weight in the ROI optimization, but with ESG fund, with de-optimization and random portfolio optimization, the ESG fund is getting a very high weight. So it probably is due to difference due to optimization scheme. Now let us plot a very important plot of overall picture of this optimize. So we have created an overall portfolio objective. Let us visualize that. So we'll create plot of feasible portfolios. For that we'll make use of good old plot command and max sr. So we have already our object portfolio object ready with us, only that in the risk call we have standard deviation because this was Sharpe ratio, so this measure is standard deviation. If you want to see all the assets in the plot, then you need to put chart.assets as true, so all the assets will also be shown, and the central heading is optimize portfolio plot with ROI. So let us, and before printing I'll also create the other three, which is D based with D and with random portfolio RP, with random portfolios random. So I've created these three plot objectives, plot commands. Let me just show you how these plots appear. So I'll start with the ROI. Let's see. So just have a look at this graph. Now with one caveat that in this optimization the portfolio, the 2000 portfolios were not simulated, so only you can see the optimized portfolio on the risk return diagram. So on y-axis you have mean, which is average return, and on x-axis you have standard deviation, so you can see your optimal portfolio along with other assets. And on the bottom chart you have weights, you can see the highest weight given to UA futures as per ROI schedule. In this case you do not see the entire feasible set of portfolios because they were not part of the optimization. In the other D-Optim schedule you'll find them. So as you can see in D-Optim you can see all those points, right, those portfolios that were simulated. You can also see the slight bit change in the optimal portfolio location, which is different from the previous one. And you can see all the other plots, UA futures, Bitcoin and their positions also. In this case ESG fund gets almost 80% of the weight, and the location of optimal portfolio vis-a-vis other four assets is provided. Next I'll show you the random portfolio. Again, with random portfolio you can see the optimal portfolio is almost at the same equation, which is different from ROI, much different from ROI. Again, ESG funds get almost 80% of the weight. Location of other assets will obviously remain same in their position on the mean and standard deviation, mean variance graph. You can also see equal weighted portfolio in yellow somewhere at the center of this feasible portfolio region. So this region where all the simulated portfolios in the form of circles are there is called feasible region. These are all feasible portfolios based given under the constraint and objective functions, the constraints that we have provided. And we can see the optimal portfolio here and ESG fund and so on. Let us also add to this plot another couple of interesting plots. So we'll also add chart the risk reward diagram. Let's see how it looks. So we'll try to plot the risk reward diagram. So let's draw this risk reward diagram with our max SR objective. So ROI, and again our risk dot call equal to standard deviation and return dot call is mean. Also because there'll be three plots, so I'll just add this par mflow as 3. Now all I need to do is I can reuse the same and just add DE, and the third one for us is random portfolio. Let us see if we are able to plot them without any error. So the three commands I have written for these three different plots. Because of this par mflow command, three plots will be plotted on the same plot window. So you can see the three plots. You have on y-axis you have mean, on x-axis you have standard deviation. Only that in the first ROI optimization schedule you will not have those simulated portfolios which are there in other three. Let me add the name also to make them better. So I'll add the central heading as maybe ROI, ROI based optimization. Now for others, I'll reuse this d-optim based optimization. So now my plot will be slightly better. Otherwise, it was not making much sense whether which kind of optimization is used in different plots. Random portfolio based optimization. So now the graph will make more sense. I hope so. So let me just and let's pull all three of them. So you can see ROI based, not other feasible portfolios are there, but in d-optim and random portfolio based optimization, you have the optimal. You can notice the optimal portfolio location is very identical in D based and random portfolio based as compared to ROI. And the reason being the composition of individual assets were very different. While similar in d-optim and random portfolio, it was very different in ROI based. So that's why the location of optimal portfolio is also very different. Optimal portfolio in a sense means that the portfolio which maximizes your Sharpe ratio under different optimization schemes. To summarize, in this video, we visualized the optimized portfolio objects and saw the weights and composition of the optimal portfolio through visualization. In the next video, we'll conclude this Sharpe ratio maximization with charting of efficient frontier and visualization of the same. In the previous video, we have computed the optimized portfolio and visualized their weights and some other attributes. In this video, we'll see how to compute the mean variance efficient frontier for Sharpe ratio maximization. So in the previous video, the measure was Sharpe ratio, which is price of risk per unit of risk. So in this video, we'll try to compute efficient frontier for that. So this was on mean variance. So we'll use the name of the object for simplicity mean var.ef because the efficient frontier is created for mean variance object. The function that we are using is create efficient frontier. First, you need to supply the return object, which is R, which contains the return of assets. Then if you recall, for Sharpe ratio, the portfolio object that we created was sr.portf. Type, this is kind of mean standard deviation, which is our risk measure. This is the optimization. Now you can also provide number of portfolio that you want to use for this optimization take place. 25 in my experience is a good number. So let's run it. Simultaneously, you can also print the object that you have created. For example, if I print this object, you can see here mean, standard deviation are the objectives and it has these constraints. We can also summarize this. So let's just summarize the object that we have created. Summary mean var and digits to restrict the digits to 2. So you can see, maybe you can see some of the measures being computed here, the weights for efficient frontier for the 25 portfolios and risk return matrix. Probably if I put digits as 4, maybe I'll get something. Yes, so we get the risk in here, we get the mean standard deviation for different portfolios. Now that we have computed this object which contains the 25 efficient portfolios on the efficient frontier, let us chart it. So we'll use this chart dot efficient frontier function. Now here you have to supply the object that you have created and you have to also supply the risk measure, which is standard deviation in match.call. So this will use the name standard deviation. Now I can have a type as well. We can change this type as well later. And if you want to change the heading, you have to use this RAR is for risk adjusted return. So if you do not provide it, the default is modified Sharpe ratio. If you want to provide, as in this case, the risk measure is Sharpe ratio only. Also for plotting these efficient portfolios, for me PCH4 works well. You will see the shape of those. So you can see how the PCH4 gives you these dots. So you can see now the efficient frontier is there and the tangent line, assuming RF equal to 0, which is the risk-free rate, is given. Your Sharpe ratio comes out to around 6.49, which is the price of risk, that is per unit of risk, how much return or risk premium you're getting. In addition to that, you have also, you can see here UA futures, the location of bit, Coin, ESG fund, S&P 500, all the assets, their location is given. And on this feasible frontier, you have the efficient frontier here. The mean or expected return or average return is on y-axis, standard deviation on x-axis. And this is your efficient frontier. The tangency portfolio is also shown here. You can also chart the asset weights. For example, let me show you. So you can write this. You can chart the asset weights along the efficient frontier. You can increase the size of label with sex.lab. We'll see that. So you can chart the efficient frontier weights by writing this mean var EF, and you can provide again the match.call argument will use this argument standard deviation. Now if you want to decrease or increase the size of your labels, you can use main. So for central heading, this main I'm using empty, and then you can use this sex.lab for size. For now, let's keep this as 1 and see if it suits our taste and preferences. Otherwise we'll change it. Yeah, so it looks better. So you can see the weights of all those efficient frontier portfolios. You can see starting from this, and we can see as we move ahead, as we increase the risk, the weight of UA future increases as we go further up here, different composition. So on the portfolios that are on efficient frontier, those 25 portfolios, their weights are shown, and we can see how the weight, the black color is for Bitcoin, so its weight remains mostly steady at a very low level, while S&P 500 weight fluctuates a lot. It increases and then it decreases. Then ESG fund is in green and blue one is UA future. So you can see, and there are three axes presented. For example, on bottom axis you have return, on top you have risk, and on vertical axis you have weights, and how these weights are changing with risk return portfolios. Each portfolio is, there are 25 such portfolios, and each portfolio you can see the combination of return, risk, and the composition of individual assets. So to summarize, in this video we saw how to compute the efficient frontier for our mean variance framework, in this case Sharpe ratio based mean variance framework. And we also visualized the efficient frontier. We computed 25 portfolios that are part of efficient frontier and what are their compositions in terms of weights, that also we visualized. In the previous video, we maximized Sharpe ratio where risk measure was standard deviation. In this video, we'll maximize star ratio, which is stable tail adjusted return ratio, which is very similar to Sharpe ratio, only that here the risk measure is expected shortfall, or what we call as conditional VAR or C VAR. So we'll maximize the star ratio here. Let us start with the objective, which is max star. We'll use this max star dot portef, and again we'll have to specify our objective, add objective, and as we did earlier, we'll use this initiate dot portef, type as return, and name equal to mean. So this is our return objective, first objective. Again we'll just copy paste it, and please don't forget to replace the portfolio object, because we are augmenting, not replacing, but augmenting our max start portef object. And here now the risk measure is our ES, expected shortfall, or what we call as conditional VAR. But this is this measure runs on certain confidence level, so you have to specify. By default 95% confidence is used, but you can specify that with this argument a different value can also be used. Now let me print this. So if you print this object, you can see here there are two objectives, mean and ES, and they will be simultaneously optimized when we'll go ahead with the optimization scheme shortly. So let us start with the optimization scheme. I'll copy paste the same, I'll not rewrite the entire thing, I'll just copy paste the optimization schedule. So very few changes will perform. So in the optimization schedule, first we'll use max star, we'll replace this, and we'll make use of our max star portfolio here. So just remove this. And this is our first objective. Let me run this optimization schedule, max star object, and when I run it, I'll also show you the weights and the portfolio objects. So you can see the weights here: 14% to Bitcoin, 6.24 to S&P 500. ESG fund is getting the minimum 5%, and EUA futures are getting close to 75. You can print the full object where the return, which is 0.16, expected shortfall measure, which is 5.64%, is being calculated along with the weights. You can see the full object here, all the parameters. Similarly, I'll use the DE optim. So I'll again copy paste this max star because we are using the DE optim objective. So portfolio object max star need to be pasted at this SR portif, if you recall. So we'll just, other parameters will keep as same, only this max star will be removed, and we'll run this up. While this optimization schedule runs, we'll just slightly tweak our codes to print the object. The optimization schedule has run quite quickly, so we'll see the object again: 5% to Bitcoin, 8.46 to S&P, 5% to AG, and 5.8 to EUA futures. Let us print the full objective. So we have, okay, so this, in this case, you can see the return measure, which is 0.05%, and expected shortfall as 6.4%. They are slightly changed. We can see the optimal portfolio weights in this particular scheme. Let us go ahead with the random portfolio optimization schedule. So again, as we do, we'll just copy paste it, and we make use of maxr portef object. We'll paste it here. Small tweak of code so that we don't have to rewrite the entire thing again. Maxr, this needs to be removed, and we'll run the optimization schedule. It will take a few seconds maybe. So meanwhile, we'll adjust our codes to print the object. So the code has run. So let's see the weight. So again, 5.2%, 84% to S&P 500, and close to 5% to all the assets. We can print our full random portfolio objective. Again, very similar to DE optim optimization. So again, we are seeing it again that DE optim optimization and random portfolio optimizations works in a very similar way. So the weights assigned to assets and our optimal portfolio objective is very sort of similar to DE optim with random portfolio, while different from ROI optimization. So in this video, we constructed our max star or stable tail adjusted return ratio, which is a combination of return and expected shortfall or conditional VAR measure. So both of them together optimized the risk and return, and we computed our optimization objects based on random portfolio, DE optim, and ROI methods. In the next video, we will visualize these objects that we have created. In this video, we'll visualize our star optimized objects. So in the previous video, we optimized portfolio for maximizing star ratio, and in this video we'll perform the visualization exercise. We'll not rewrite the full codes, we'll make use of the previously written codes. So let's just start by copy pasting the previous codes. We'll just copy paste them, and let us start one by one. So first, let us start with the weight visualization plot. So here, instead of max SR, I need to conduct max star for ROI. So this is max star objective, and here we are max star with ROI. The next is max star D. So I'll change the name accordingly. So it's very identical set of codes. We are using the same code with the minor tweak. So with a minor tweak, we have adjusted our portfolio objects. So let's start with the visualization exercise. So we have the three plots here in front of us. Notice when we focus on our portfolio object, you can see here that with the optimization schedule has resulted in a different portfolio with ROI as compared to DE optim and random portfolio. So in ROI plot, you can see the maximum weight to EUA future close to 80%, while with DOptim and random portfolio, the star object has highest weight to S&P 500, which is close to 80%. Let us also modify our object with the bar plot. So let us visualize with the bar plot as well. So all I need to do is I need to just make use of these same codes. I'll just modify them a little bit. So first I need to add plot dot type as bar plot, and legend, if you recall, this used to be null. So now I need to just copy paste this thing, and now we are good to go. So we'll just plot them, and this the same plot will result, but it's just a different way of visualization. You can see all the three plots, but in a bar plot form. The same inferences, that 80% weight for UA futures for max star with ROI, while DOptim and random portfolio results in 80% to S&P 500. So a very nice aesthetic plot has resulted. Next, we'll plot our feasible portfolios. The trick is to again use our good old portfolio max star object here. So max star object, and in this max star object, the risk measure is ES, and optimize portfolio plot with ROI. Risk measure is ES. So we'll see one by one. So all the three plots. So first max star, and notice here in the optimum portfolio you can see there is no feasible portfolios because this is ROI optimization that will come in the DOptim and random portfolios. But you can see on the mean variance framework, the risk measure is ES on x-axis, on y-axis we have the mean. Optimal portfolio is this blue one, and we can see its position. You can also see the UA futures in the bottom. You have the weights, and UA futures have almost 80%. Now if I run this with DOptim, you have feasible portfolios, and the position of optimal portfolio has changed, and the 80% weight is now with S&P 500, which we saw earlier also. The position of other assets like UA future on this mean and ES diagram will remain same because they are individual assets, so their position will remain same, but optimal portfolio has changed because the weights are different. For random portfolio, if I run, now I have run with the random portfolio. Here with the random portfolio, you can see the portfolio with DOptim is quite similar. It is quite similar to DOptim. The yellow one is on the top diagram. You can see the yellow one is equal weighted portfolio. In the bottom also you can see with yellow one the weights are identical, 25% to all the four assets. The position of optimal portfolio is very similar to that with DOptim here, and you also have set of feasible portfolios plotted for you. Lastly, let us also plot the risk reward on the risk reward diagram. So a minor tweak again, we'll use our max star objective here, max star objective, and I'll slightly change the standard deviation to E. Otherwise we'll not get those feasible portfolios, so we have to make use of our empty kind of diagram. So it doesn't look good aesthetically, but still in the interest of comparison we'll just plot it. So we'll have this max star objective with this caveat. We move ahead, and let me show you the diagram. So let us print our objectives, and now we have three diagrams. You can see the position of optimal portfolio is very similar in DOptim based optimization and random portfolio optimization. However, with the ROI based optimization, there are no feasible portfolios, so it's not very meaningful, but still you can compare the location of optimal portfolio. The optimal portfolio with ROI is very different because of obviously the constituent weights are very different in DOptim and random as compared to ROI. We can see their relative positions on the mean ES diagram. So on the y-axis you have average returns or mean returns, on x-axis you have risk. You can see the optimal portfolio has much lower risk in the Optim and random portfolio, while a higher risk but a higher return on ROI based optimization. In addition, a very interesting diagram is the concentration diagram that I would like to show. So concentration of asset. Now the trick here is to make use of this very interesting function called chart.concentration, and in this I'll provide our max star objective. So it is only because there are no feasible portfolios for ROI, so this is only available for DE. In constant type, we'll put weights. You can have percentage contribution also, but we'll use weights for now. Weights, you can check other parameters with the help window. We'd like to plot assets as true, and let us run this. So before running, I'll also write the same code for the other one, which is random portfolio. So I'll show you both of them. First, we'll run the DE-optim based. So you can see as the degree of concentration increases, on the top you have all the feasible portfolios with y-axis being average return and x-axis being the ES risk measure. You have individual assets also being plotted, as you can see. And on the bottom diagram, you have increasing concentration. And as you would have expected, as the concentration increases, the risk increases. So we can see the concentration increasing along with the risk. For example, the ones on the far right will have very high concentration and also those extremely risky portfolios. The same if I run this for random portfolio, there's minor changes and you can see the concentration moving with the portfolio risk. So you can compare how with concentration as you keep increasing. The formula for this concentration you can check. It is something like summation of squares, summation of weight squares. Because weights are in percentages, their squares will be summed up and added to give you this concentration. You can check for on the help window for the exact computation of this concentration level. To summarize this video, here we visualized the portfolio object created for our star, which is stable tail adjusted return ratio. So for that star optimized portfolio, we computed the optimization of objects and then visualize them. Particularly, we visualize the chart weights for portfolio weights. We also visualized on the feasible frontier, the feasible portfolios. And lastly, we also visualize the concentration plot. In the next video, we'll visualize the efficient frontier. In the previous video, we visualize various attributes of our star portfolio object, which is optimization or maximization of star object with return to expected shortfall risk ratio. In this video, we'll compute the mean variance, or rather mean ES, I would call it mean ES efficient frontier. We'll compute it and visualize the object. So first let us start with the computation of mean ES dot efficient frontier. So for that we'll make use of the efficient frontier objective. Again, we'll provide our asset object R, and recall that for the portfolio we have already specified our max star portfolio object. In this case, the type, as I noted, will be equal to mean ES. So let me just put it like that. So the objective is of mean ES type. This is the type of optimization we have done. Again, for a efficient frontier, you need to specify how many portfolios. If you recall, 20 portfolio works well. So we'll run this. Now, first and foremost, now that we have created our mean ES efficient frontier objective, let us see what is there inside it. So we'll print it. You can see two objectives, mean along with risk measure of ES, and then there were constraints, weight sum constraint, box constraint, and group constraint. So you can also print summary of it, and in the summary, mean ES objective will provide digits. We know that it would be good if we provide 4 digit. So when we print it for all the 25 portfolios, we have the weights. You can see their weights, and these are 25 points. You can also see their risk return. Risk is mean and expected shortfall. So while plotting, these attributes will be employed. Let's start plot with our efficient frontier plot. So first and foremost, let us write the code. So the code that we used was chart.efficient frontier, and if you recall, in the previous code we provided this mean ES object along with match dot call. In the previous case it was standard deviation, in this case this is expected shortfall. The risk measure, the type we are using line type, you can also choose box type or other types, you can check on the help. For RAR text, which is risk adjusted return, we are in this particular case we would like to use star ratio. Previously we used Sharpe ratio, in this case we would like to use star stable tail adjusted return ratio. And PCHS4, you can change this PCH also, but PCH4 works well for me. So let me plot this. So let's see. So this is your efficient frontier. You can see the tangent line. You can see the star ratio of 0.0284, risk free given risk free rate of 0. On x-axis you have the expected shortfall or CVAR measure. On y-axis you have expected average returns. Individual assets are also plotted. You can see the tangency or optimal portfolio and the efficient frontier as well. Now, if you recall, the next step was to plot the efficient frontier weights, and for we'll plot the weights of EF portfolios. How to do that? So we'll make use of this chart EF weights command, where we need to provide our mean ES object. Again, in match dot call parameter we have expected shortfall, and central heading will use as empty. Again, sex.lab parameter can be taken as 1. It gives you the size of access label. So let us run this code. Let's see what do we get. So here you can see the weight composition of all those 25 portfolios. On the bottom you have their return, on the top you have their risk and their weight composition. So you can see the changing weights. The green one is ESG fund, the red or maroon one is the S&P 500, the black one is Bitcoin, and blue one is UA futures. As you can see, as the risk return profile changes, how the weight composition changes across all the 25 portfolios very nicely. So you can analyze that. So to conclude, in this video we computed the efficient frontier. We plotted the efficient frontier. In the previous diagram it appeared like this. We had the tangency line, the star ratio. So in this efficient frontier the risk measure is expected shortfall. So we plotted on mean ES diagram, we plotted the tangency portfolio and efficient frontier using those 25 portfolios, and then we also saw their weight composition using chart EF weight function. In the next video, we'll conclude our portfolio analytics exercise by visualizing and computing the combined optimizations. Recall that we have previously created two objects, one with maximizing star ratio and one with maximizing Sharpe ratio. And each of these optimizations are performed using DOptim method as well as random portfolio method. So in this particular video, we'll perform combined optimizations. We'll try to compare all these four optimizations, two for Sharpe ratio, two for star ratio, by combining our optimization objects. Let's see how to do that. So let's start. So first is optimization with D schedule. So here we'll make use of this combine optimizations function, and we'll put it in the form of list object. First we have mean SD, where our objective was to minimize the standard deviation with D. Then we had mean ES, where we had minimized the ES objective with D. Next we had mean, keep this, so we have mean SR, which is maximize Sharpe ratio objective, and then we have mean star, which has maximize star D. So this was for D, and similarly we had another one for random portfolios, wherein for standard deviation objectives we had random portfolio. For all the ES also we had random portfolio. So we have two for RP also. So these are random portfolio optimization. So now we have created two combined optimization objects. One is for D schedule, one is for random portfolio. In the next we'll extract the object parameter. So we'll extract object parameters from each combined each optimization object. Let's see how it is done. So we'll make use of op optimize D and let's call it object D, which require extraction of extract objective measures function, and in this case this is object, and we use opt underscore D. So this is first, and if you recall, the second one is for random portfolio. We'll run this as well. So this is random portfolio. Now we'll extract weights. So weights underscore D, which is extract. So we'll write heading extract weights. Weights function. Here we have opt. We'll also extract for random portfolios. We'll make use of these shortly. So let us first print them one by one. So first let us print object D. So when I print it, you can see object.d carries standard deviation, mean, and expected shortfall for all these four measures. Object D, similarly I can print for object RP. You can print for object RP also, and all these parameters will be given to you: standard deviation, mean, and DS. For RP, for all the four configurations, mean SD, mean ES, mean SR, you can see the standard deviation measure, you can see the mean, which is average return, and ES measure. Similarly, I can extract the weights for D. Let's see the weights. You can see the weights for individual assets for each configuration: Bitcoin, S&P 500, ESG fund, UA futures. You can see for mean SD, mean ES, mean SR individually. You can compare the weights, and the same you can do for random portfolio optimization. You can print the weights. Let us carry out the visualization exercise also. So to visualize, first we'll visualize chart weights. So chart dot weights. For that, I'll use first for D, and let us so to ensure that, because maximum access can go up till 1, maximum weight can go up till slightly higher than 1, in fact, but let's see. So this is for of D. Let's visualize the weights. We'll write the heading as visualize the weights. So this is the full command. As you can see here, this is our full command, but we need to enlarge the plot window to visualize. You can see the movement here. So you can see for all the configurations, mean SD, mean ES, mean SR, mean star, you can see how the weights are moving across different assets. The same you can do with RP object. You can see with the RP object. Also, in another fashion, you can plot it. What you can do is you can change the plot type. Currently the plot type is line, so you can change the plot type to bar. And let me first show you if for the D. So this is for D, you can see, and you can see for each of the Bitcoin. You can see for Bitcoin, for all the four configuration what is weight, for S&P 500 for all the four configuration what is weight, and so on. Similarly for random portfolio, you can see the weights and so on. Lastly, you can chart the optimal portfolios in the risk reward space. That is also not too difficult. What we need to do is we can use this chart dot risk reward. We have already plotted this, so I can add opt D, and central heading is optimal portfolios. Now you can also specify whether you want to have, say for example, risk.call as standard deviation. You can have standard deviation, or also you can have ES as well. Similarly, the same plots you can plot for random portfolios. I'll show one by one. So random portfolios also you can plot these. So I'll show you one by one how they appear. So first we'll do it for D with standard deviation. So you can see on y-axis we have average return, and x-axis you have standard deviation, and all the four portfolios are plotted. Now if you want to have, instead of standard deviation, you have expected shortfall, you can change it. Similarly for random portfolios also you can change it. So this way you can plot it, and the commands are shown here. For example, the first one, optimal portfolios with D optim and std dv. So this is for that. Then optimal portfolios with DE optimization and ES measure. Now the graph will look more proper with random portfolios and standard deviation. With random portfolios and ES. So now I'll again run it, and you will see the difference. Now the central heading is changed. You can see optimal portfolio with D optim and standard deviation, D optim with ES measure, random portfolio with standard deviation, and random portfolio with ES measure. So with this we have compared our optimized portfolio objectives in a combined manner also. To summarize the lesson, first we initiated the portfolio object. Then we explored how to add various constraints such as weight sum constraint, box constraints, and group constraints. Next, we optimized a portfolio with maximum returns and found the weights with the help of three optimizers, namely random portfolio, D-optim, and ROE optimizers. Next, we visualized this portfolio with maximum returns. Next, we optimized a portfolio with minimum standard deviation and found the weights using the three optimizers, namely ROI, D-optim, and random portfolio. Subsequently, we visualize this portfolio with minimum standard deviation. Then we optimize and construct a portfolio with minimum expected shortfall as risk measure, compute its weight, and visualize the portfolio. Next, we optimize and construct a portfolio with maximum Sharpe ratio measure. We also plot the efficient frontier and identify the most optimum market portfolio. Next, we optimize and construct the portfolio with maximum star ratio, that is stable tail adjusted return ratio measure. We also found the portfolio weights and also visualized the portfolio object. Lastly, we conducted the combined portfolio optimizations with all the four objects, namely standard deviation, expected shortfall, Sharpe ratio, and star measure. We compared and visualized all these portfolio objects.